We interact with Google Drive as if it were a standard local hard drive, where files sit in static folders and never move. Underneath that interface, a massive orchestration of independent services handles the live tracking of state changes, access rights, and data collisions across millions of nodes. To maintain this illusion of simplicity, the system must account for network latency and hardware failure, masking these infrastructure realities from the user interface. This architecture functions as a distributed state machine, designed to force metadata, raw bytes, and remote devices to converge on a single truth, even when the underlying hardware fails. Modern cloud storage requires that a file be split into two distinct data streams immediately upon upload. A metadata ticket routes to a central database, while the file body is fractured into uniform, manageable chunks destined for object storage. Real-world network conditions make monolithic uploads unreliable. If a connection drops during a multi-databyte transfer, chunking allows the system to recover without restarting the entire process. This transforms the upload into a resumable state machine. The server tracks which specific chunks have arrived and only requests the missing pieces when the connection is restored. Using content hashing, such as SHA-256, the system identifies identical chunks across different users. If two people upload the same document, the system maps both to a single stored copy to optimize storage space. This efficiency creates a security trade-off. If the system confirms a chunk already exists based on its hash, it can inadvertently reveal that a specific file is already present on the servers, requiring the system to carefully scope these checks. While uploads go through the API, downloads often bypass it. The system provides the client with a signed URL, allowing the device to pull chunks directly from a regional edge node to maximize speed. The central database holds the structural logic and metadata pointers required to locate and reassemble these disparate chunks whenever a user requests the file. The visual metaphor of the folder is equally abstract. Moving or renaming a folder changes a metadata relationship, but leaves the underlying bytes exactly where they were. Folders function as permissioned metadata views. Each folder is a node that uses directional links to point to specific file IDs. When you open a folder, the system sweeps across these links to verify your access. This creates a permission graph. Inherited permissions from a team folder often overlap with unique custom permissions on individual files, creating a web of access rules that must be recalculated constantly. To avoid the latency of traversing this graph for every request, the system uses flattened permission groups or materialized views to provide near-instant access decisions. A sharing link operates as a serialized permission. It carries a unique hash that grants specific tokens to the bearer, allowing them to bypass the standard identity-based graph. These permissions exist as a high-performance graph architecture, optimized to answer complex access questions for every single user interaction. Storing a complete new copy of a file for every minor edit would be prohibitively expensive in terms of both storage and bandwidth. Chunk-level versioning solves this. When a file is modified, only the edited block is uploaded. The metadata then updates the timeline to point to the new block, while continuing to reference the unmodified original chunks. Versioning defines the file state by tracking which specific timeline of chunks represents the correct version at any given point in time. Synchronizing millions of clients presents a massive scaling challenge. If every device constantly polled the server to check for updates, the resulting traffic would overwhelm the infrastructure. Instead, clients subscribe to an ordered log of mutations. When one device injects a state change into this sequential ledger, the change trickles down to other connected devices, which replay the event locally to update their state. Offline edits make conflicts a certainty. For binary files like images, the system typically handles this by forking the file into two separate copies, ensuring no user data is overwritten. Metadata conflicts are resolved through deterministic logic. The system compares timestamps in the mutation log and applies rules like last write wins to bring all devices back into a unified state. Distributed sync systems are built on the assumption that conflicts are a core property of the environment. The architecture exists to make these collisions survivable. The system confirms a successful upload to the user the moment the bytes are secured, but the broader processing of that file is only just beginning. A pub sub-event pipeline triggers several background tasks simultaneously. This allows the system to generate thumbnails, update user quotas, and index the file for search in parallel without delaying the user. Search indexing is particularly complex. The indexer must cross-reference the file content with the permission graph, ensuring that search results only appear for users who have been granted explicit access. This event-driven model ensures that heavy, non-critical processing tasks never block the primary upload flow. The system manages different data types with different consistency models. Permissions require strong consistency to ensure security changes take effect immediately, while quotas and thumbnails can rely on eventual consistency to settle over a few seconds. Every component assumes that network events will arrive late, out of order, or twice. Background workers are programmed to handle these duplications and reconcile orphan data automatically.